Hello everyone. In this video I will present 3 solved exercises dealing with the shear strength of soils. The first exercise considers the direct shear test performed on a sand. From the direct shear test performed on a sand sample of negligible cohesion, the friction angle is a given data. The question is to determine for a given normal stress sigma applied on the horizontal plane here, the values of the principal stresses and their direction at a point M that belongs to the failure plane. The reply to this question: first, we confirm that cohesion is negligible for sands, and the Coulomb's law governing the shear strength of soils becomes simply tau equals sigma multiplying tangent phi, the friction angle. In this figure we can see the intrinsic curve that passes by 0 because cohesion is 0, and the angle between the stress vector on the facet or plane and the normal to this facet is the friction angle phi. And here we can see a given failure plane, the normal and the stress vector, and the angle in between equals the friction angle. This is a picture showing a horizontal failure plane on a clay sample, and we have to focus that this angle between the stress vector and the normal to the failure plane is equals the friction angle, and we can see here the direction of the normal stress, failure plane, and here we have the stress vector, and its angle equals the friction angle of the soil. To determine the principal stresses value, we know that those stresses enable drawing the Morse circle. Then we can calculate the state of stress sigma and tau on any surface or plane. In this case, this is the Morse diagram: shear stress, normal stress, and the intrinsic curve passing by 0. And the Morse circle we are dealing with on the failure plane should be tangent to the intrinsic curve. So we need to draw the circle tangent to the intrinsic curve, and the state of stress on the failure plane, that is here, it belongs both to the circle and to the intrinsic curve. Calculation of the principal stresses. Let us consider first this triangle O, O dash, and T. This is the origin. This is the abscissa of the average stress or mean stress, sigma m, and this is sigma normal stress on the failure plane. So we can write in this small triangle that radius of the circle T O dash multiplying sinus phi, friction angle, this is 90 degrees, that is half of P minus phi, so this is phi, and we have this relationship. We substitute sigma m by sigma 1 plus sigma 3 by 2, and TO dash is the radius, that is the difference between the two major and minor principal stresses by 2. This is the first relationship. Let us consider now the big triangle OT O dash, and in this triangle we can send to right that radius TO dash, that means the difference between the two major stresses divided by 2, divided by sigma m, the hypotenuse, coincides with the value of sigma m. It is equal sinus. Fine. So from the system of equation we can determine this value of the major principal stress and this value of the minor principal stress, analytically of course. Question 2 is to compare the obtained results from the direct shear with the direction of the failure plane in case we perform triaxial test on the same sound. So the reply is, first, to remind that when we do the triaxial test, the specimen is subject, especially in failure, only the major principal stress sigma 1 subject on the horizontal plane, and sigma 3 the minor principal stress on the vertical plane. And during triaxial test we can observe sometimes the direction of the failure plane, as we can see here on this picture. So this is a specimen that was subject to the triaxial test, and here we can see the failure plane, and the direction of the failure plane with the horizontal plane is visible. From the representation of the Moore diagram, the last slide, we can easily determine that alpha is angle 4p plus half of friction angle. To answer the question, we have to say that alpha angle gives the direction of the failure plane for triaxial test with respect to horizontal. That is the direction of the major principal subject to stress sigma 1, as we can see here. For the direct shear test, those two directions are inverted. The angle is the same, but the direction of the two planes are changed. How? Let us materialize this direction of the failure plane for the triaxial test and put again the picture of the direct shear test. So as we can see here, the failure plane is horizontal, but here it is inclined with an angle alpha, this value with respect to horizontal. But at the same time, the horizontal plane becomes the failure plane. So we can see that in this case here and for the direct shear test we have the same angle. So the reply, it is the same direction that we obtained from the direct shear test that we can found using triaxial apparatus. So this ends the first exercise. Second exercise deals with the shear strength of silt soil. So after a geotechnical survey, the soil profile shown within alluvial silt layer at depth equals 15 meters from the ground surface. The soil overlaying the alluvial silt layer has a dry unit weight, the gamma d equals 15 kN per cubic meter, and an average water content of 30%. And the information is that the water table is close to the ground surface. That means all the soil is saturated. On intact soil specimens of the alluvial silt layer were subject to shear test, from which the following parameters were obtained. So the parameters are the unbrained cohesion and the unbrained friction angle. And then the effective cohesion or the brained cohesion and the effective friction angle. So the first question is to calculate the shear strength of this alluvial silt soil and the following cases. Case 1, first case, the shear phase is performed rapidly. And in the second phase, or the second option, the shear phase is performed very slowly. So as we know that when we do unbrained tests, the rate of shear is high. That means the shear phase is performed rapidly, and this corresponds to the short-term behavior or failure behavior. Contrarily, when we do blind test, the shear rate is low, quite slow, and the result obtained refers to the long-term shear strength. As a matter of fact, we have to say that the CU and phi U correspond to the unbraided case, and C dash and phi dash correspond to the brain test. Respectively, the first one corresponds to the short term, and the second one couple correspond to the long term. So let us calculate the shear strength in the two cases. Shear strength is governed by the Coulomb's law, that is in general this one. So consider the short-term case. Calculation is done using total stresses. And total stresses, after Vertesagi's postulate, it is the sum of the effective stress plus the pore pressure. So when we substitute the C and phi corresponding to the short term, we obtain Cu plus tangent Vu multiplying sigma, that is total stress. So when you substitute sigma by the sum, we get the sigma dash multiplying tangent Vu, but we will have U multiplying tangent Vu. This term is 0, and we have the U. That means we cannot have some friction in water because the U is pore pressure, and U multiplying tangent U is 0 because there is no friction angle, you can say, in water. This anisotrophic pressure. Now, considering the long-term case, this Coulomb's law become an effective stresses totally. So we have C dash plus the effective stress, not the total, the effective stress multiplying tangent phi dash. So the calculation now, so for both cases, short term and long term, we have to calculate the effective stress. We can see here effective stress. So effective stress is the total stress minus pore pressure. The total stress is simply, for the considered case, we have 15 meters overlaying the silt layer. That means we have gamma, but gamma is gamma d, the dry unit weight multiplying 1 plus omega, the water content, and it will be 15, the gamma d, 1 plus 30%, that is 0.3, 1.3 multiplying 15 meter, and the result is this one. At the same depth, water pressure will be simply 10 by 15, 115 kPa. So the sigma dash is the difference between those values. It will be 142.5 kilopascal first. So for the short-term shear strength, the result will be 15, that is Cu, plus sigma dash, that is this one, multiplying tangent 30 degrees, plus the pore pressure, 100 is the pore pressure. We obtain by 233 kilopascal. Whilst for the long-term shear strength, we have this equation. So C dash is 40, T dash is 23, and the sigma dash is the same one, 142, and the result will be 100.5 kilopascals. So we can simply remark that the shear strength in long-term case is quite small than the one obtained at short-term case. This corresponds especially to clays having C dash. That means C dash is positive, which correspond to over-consolidated clays. So now the third exercise. Let us consider the profile of the soil mass represented in this figure, and we can see that we have a fill layer of 2 meter thickness and then a clay layer with high thickness, and we know that the undrained cohesion of the clay layer at 3 meter, that means 1 meter below the ground water table level here, is Cu 15 kilopascals. So the question is to determine the values of the total principal stresses of a consolidated undrained triaxial test performed on a clay specimen extracted at 8 meter depth. 8 meter depth, that is 2 plus 6 meter. So here I put 5 meter, but we need to calculate at 8 meter, so this should be 6. So note that for this clay we have the total unit is 16, and the tangent lambda Cu, the increase in undrained cohesion, is 0.2. So the reply is principal stresses sigma 1 and sigma 3 to draw the Mohr circle. So sigma 3 is the consolidation stress, and by definition the consolidation stress is an effective stress. So we need to calculate at 8 meter the effective stress that correspond to the consolidated undrained triaxial test performed on the specimen taken at 8 meter depth. So as we can see, the effective stress directly is the total stress minus the water pressure, but it can be simply written because this soil is unsaturated. So it will be 20 by 2 plus the gamma dash, total gamma minus 10 of water. 16 minus 10 becomes 6. So 6 by 6. Calculation is okay. So the effective stress at 8 meter is 76 kPa. That is the consolidation stress by which we perform the Cu test at the specimen. So this is the calculation of sigma 3. Second phase, coming back to the drawn Mohr circles for a Cu test. So we know that the Cu for each test is simply the radius of the circle. And since we consolidate the soil from a test to another, That means the shear stress increases. And this ratio tangent lambda is the increase of Cu, that means the radius of the circle, when the consolidation stress increases. So the unbraid cohesion depends on depth, because depth is referring to the consolidation stress, that is the effective vertical stress. So we know that at 3 meter, Cu is 15 kPa. So let us calculate the effective stress at 3 meter, as we did for the one at 8 meter. So it will be 20 by 2 plus 6 by 1, 46. If I need to calculate the unbraid cohesion at 8 meter, and knowing that the effective stress at 8 meter is 76 kPa, using this equation of the increase of Cu with depth, so we can write that tangent lambda is the difference of the unbraid cohesion at 8 meter minus the one at 3 meter, delta Cu, that is Cu at 8 meter minus the one at 3 meter, and we will divide it by the difference of the consolidation stress between the one at 8 meter and the one at 3 meter. And this is 0.2 because it is equivalent data. So the unknown is here, and from this equation we can calculate the Cu at 8 meter. So Cu at 8 meter is equal to 21 kilopascals. So as you can see, the Cu at 3 meter is 15, but at 3 meter is 15, and at 8 meter it becomes 21. That reduces the increase of Cu due to the depth, due to the consolidation. Of course, since the radius is the Cu twice Cu, the diameter is twice Cu, or the radius of the circle is Cu, so we can write that sigma 1 is twice Cu plus sigma 3, and this is the value of sigma 1. And as such, we respond to the question, calculate the total principal stresses, sigma 3 at 8 meter and sigma 1 at 8 meter. So we have to note that at the end of the consolidated unbraided test, the sigma 1 and sigma 3 in the failure phase become total stresses, because the shear phase is performed in unbraided cohesion. That was mentioned in the first question. When the shear phase is performed rapidly, we are in unbraided cohesion. And therefore, the difference between the unconsolidated unbraided test and the consolidated unbraided test resides in the consolidation phase, that is, prior to the failure phase. If the soil is unconsolidated, Cu is almost constant, and in case the soil is consolidated, the Cu increases due to the consolidation. As such, this video is ended, and thank you for your attention.